All right. So the plan for today, so lecture 3. So I said right in the beginning that we will focus on 2 types of approximations, the Runge type approximations and Mergelyan type approximations. So I think for now I've said what I wanted to say about Runge type approximation. So today we will move on and talk about the following. So I'll just recall this notation. So A of k was the space of all complex valued continuous functions on k such that f is holomorphic in the interior of k. Okay, and there are actually 2 cases that are sort of, I mean, when you study this kind of a problem, there are 2 interesting cases that one tends to focus on. One is where k is the closure of a bounded domain, or let's say open set. And the other one is when the interior of k is empty, in which case, of course, we are just looking at all continuous functions on k. Okay? So when I refer to Mergelyan type approximation, I'm basically asking, you know, when can I say that A of k is either P of k? So either all of these functions are uniformly approximable by restrictions of holomorphic polynomials or rational functions. And today, we will only focus on the planar case, because as always, we can say a lot more in the plane. And so today it will be quite analytic, and then tomorrow I will switch to what we can say in higher dimensions. We can say a lot less, so I'll focus on a very, very special case tomorrow in both the lectures, and that will be a much more geometric discussion. So I wanted to say something over here. I need to make sure I say right. So today we are only working, so this is compact in the plane. And I just want to start with 2 examples. And I'm not actually going to give you the details. These are exercises. They're not that hard, but it's worth thinking about. So the first is where k is the closed unit disk. And we already checked that O of k is sitting inside P of k, but that same argument doesn't quite work for this. So you have to modify the argument. So show this is an exercise, and try to use as elementary tools as possible. Just what is sort of the most basic example you can give to show that, in fact, we have this nice polynomial approximability. Okay, so this is one exercise. And the other one, which of course should not come as a surprise, but this is also worth thinking about, just using some basic tools. So we've already seen that holomorphic functions here are not approximable by polynomials. We already gave an argument for that. So of course we cannot expect this, but what we do have, we have rational approximability. Okay, so go back and think about how you can rigorously establish these 2 facts. But to sort of emphasize, so this may sort of suggest that this problem is no different from a Runge type problem. It seems like the reason I've given you these 2 seems to suggest that I'm heading in the same direction as I did with Runge approximations, but the problem is more subtle. So I'm going to say 3 things. So let me write down 3 theorems, and they're not in chronological order. And the last one I'm actually just going to write in words. I'm not really actually going to give you any math over there. So this is, I don't know, is this pen okay? No? Okay. I'll try this. I was trying to. Is this better? Okay. Great. Sorry about that. Oh, you found the stash. Okay. Thank you. I'll just keep it in my pocket. Okay, so this just says that if C minus K is connected, then in fact we can do better than Runge's theorem. We can also get polynomial approximability of the smaller class over here. So that's good. However, and this is an older result, states. So you might think, okay, now we are going to have a rational version of the same theorem, but there exists a compact set K such that we do not in general have rational approximability. Without additional conditions, we do not have rational.
Just a problem on notation. You have the
Yes.
same AK for the different things.
I have same AK. No, what I meant to say over here is we often focus on two special cases. So K in general is just a compact set. And I'm just saying that, so in one dimension there are complete characterizations, but in higher dimensions there are sort of two special cases that we tend to focus on. One where it's the closure of a bounded open set. But if there is no interior, then this is no condition. What?
Last line, you have two. There is AK, PK over RK.
Oh, or I mean, in the sense, the problem is.
Oh, no doubt.
No, there's no quotienting happening here. Yeah, okay. Sorry. Yeah, that's, it's just, yeah. Sorry about that, yeah. Thanks. Oh, yeah. So I didn't quite complete what I was saying over here. Right. No. Right. So what the whole point of this theorem is to tell you that this doesn't quite work like it does for Runge. And of course, there was a lot of attempt to understand what one really needs over here, because with, at least in the one-dimensional case, you expect to have complete characterizations. And I'll not, if I get time today, I may tell you the statement over here. I'm not going to give the statement right now. And there are a couple of results over here. So Vitushkin gave a complete characterization of complete characterization for AK equal to RK. And this involves something known as analytic capacity, and so it will take us some time to define that, and I don't want to get into that right now, but it's quite a complicated theory, and it's quite subtle. We'll see maybe we'll see some version of this or something like that. Okay, so let me just pause and see if there are any questions about the statements themselves.
And both the second two theorems are in several variables.
Both these?
Yes.
Oh. No, absolutely not. Today we are only in, yes, today we are in one dimension only, yes. I mean, we cannot say such things. I mean, these are just very general. We won't be able to say this in higher dimensions. Okay? Any other? Okay, so I don't even know if I'll get to state this. I'm going to discuss this example first. We'll describe how this goes. And then again, this is a slightly involved proof, and there are different ways of going about it. There is sort of a functional analytic proof, which is more abstract. There's a constructive proof, and I'll give references for both in the notes. But I'll do a very special case of this, and I'll sort of use the functional analytic approach because that's sort of more general, and it'll also give you a hint for how you can prove Runge's theorem. Remember, I never actually proved Runge's theorem for you. So if you want to prove that, then this approach will be useful. But we'll start with this. Okay, so we'll start with rods, and this example is referred to as the Swiss cheese, and you'll see why. Okay, so let's do the following. So the construction goes as follows. So we'll start with the unit disk. And so the idea is, when you sort of start trying to understand approximations, you try to first maybe assume that your compact set is nice. Maybe it's the closure of a nice, smooth domain. You sort of gradually realize where the problem lies. And the problem is going to be when the complement of your set has infinitely many connected components, okay? And so we are going to have to construct this set by creating infinitely many connected components, but they have to be done in a clever way so that you can actually show the failure of this. And the way we are going to construct this, we are actually going to construct something which has empty interior. So this class just becomes CK, but that's not the source of the problem. You can modify that example and also create examples where the interior is non-empty. So that you can take as an additional exercise. So let's start with this construction. So let D naught be the unit disk. And now I'm going to select, so choose, or rather let me say it this way because it's not immediately obvious, but we want a collection, a countable collection of points in D and some parameters Rj, so these lie between 0 and 1, such that if I set capital Dj to be, so this is, I don't think I have used this notation before, but let me, you can actually guess what this is. So this is just all, it's the disk of radius Rj centered at Aj, the open disk. So if I set Dj to be this disk, then the following properties hold. Okay, so first of all, the closure of each of these disks lies inside the unit disk. We want this to happen. We want these to be mutually disjoint, the closures of these to be mutually disjoint. So for all j not equal to k starting from 1, D0 is the unit disk itself. We also want that summation Rj from 1 to infinity is less than 1. You'll see why this is, why we arrange it to be so. And finally, we also want, so what is our set going to be? So I'm going to remove a bunch of disks. I will justify to you why we can do all of this, but what we want finally is that we have all these disks. Our set is going to be that we take declosure and we remove all these disks from it. And this has empty interior. So we want to arrange for this, all of this to happen. Okay? So the picture is going to look something like this. You're going to end up removing a whole bunch of disks, and therefore it is known as the Swiss cheese. There are, by the way, many variations of this. This kind of construction is a very rich source of examples in this field. And in fact, I mean, if you look on the archive, I mean, even in the last year, somebody had posted a paper about the sharp Swiss cheese. So like people are like working. And in fact, I met this mathematician, Joel Feinstein from University of Nottingham. He likes the Swiss cheese so much that his Twitter profile picture is that of this. And he was very happily telling me about this. So he's very fond of the Swiss cheese. But for us, I mean, there's a reason this is so interesting. So let's talk about why we can do this. So how are you going to construct this? So how? So we'll start with a countable dense subset. And we start with some sequence of parameters in 0, 1, which satisfy the condition that we want out of Rj's. Okay, and then the first step is, so A1, for A1, we choose B1, and for R1, we choose, so let me draw this picture here. I have D, I have some point B1, that is my A1. I need to make sure that this disk is, the closure of this disk is sitting inside the unit disk. So I need to make sure that this distance, so I'll take minimum of S1 and the distance of A1 from the boundary, which I can write differently, but I will write it like this. Okay, so I get something like this. And so okay, so we've already defined what D1 is. Okay, so once we have done this, how are we going to choose A2? So of course, I've taken a countable dense subset, and it could happen, so this is B1. It could happen that B2 is in here, B3 is in here, and so on. So for the next step, so let J0 equal to the minimum index J such that Bj is not in this closed disk over here. So just go down this sequence and just pick the first guy which lies outside this disk. And so that you set as A2. So A2 is Bj0. And how do I choose the radius? Well, remember, what all do I need to do? I need to make sure that this disk, the new disk that I create, so let's say I find my A2 over here. I need to make sure that the new disk is contained inside, the closure of that is contained inside the unit disk. It's disjoint from this, and so on. So what I do is I set R2 as, so I have this auxiliary sequence over here, S2, I use that. And then I make sure everything else happens by, first of all, making sure that I do not exit the disk, and I also make sure that I don't touch this disk over here. So A2 boundary of D1. Okay? So I just inductively do this. I'm not going to write down the inductive. Yeah, so, yeah. Okay, by two. Let's just, I mean, everything you could do half outside, sorry. Yeah, so that's fine.
Even the first disk is not allowed to touch the boundary?
Even the first disk is not allowed to touch the boundary. Okay. I really want that the closure is sitting inside the open disk.
You suppose that R1 is less than S1, S1 is less than 1, so it's okay.
S1, R1 is less than 1, yes.
And S1 is less than 1, too. So there is no problem.
S1 is less than 1 over 2.
No, it's less than 1.
Yes.
The sum is less than 1. So the S1 only is less than 1. So there is
No, but A1 could be anything, right? So A1 is just any point on the disk.
Yes.
Okay, so that's the problem. So that's why I need this piece over here. Yeah. Actually, that reminds me, I did want, okay, I'll mention that later. Yeah, so you need to make sure that the boundaries are not touching, so we just go half or whatever, you just want a little less than that, and so you proceed inductively. Okay, so by our construction and what Stephanie just said, that we are creating our J's in a way that definitely 3 will be satisfied. I mean, 1, 2, and 3 are by construction. So 1, 2, and 3 are by construction or hold by construction. I think this pen is already. Okay, so what about 4? So we need to make sure that once I throw all these disks out, once I throw all these disks out, I really don't have any interior left. So suppose not. So suppose there exists some z that lies in the closure of the disk minus all these disks that we have constructed over here. Okay? Yes, suppose there is something in the interior. So that's what we want to say, that this cannot happen. Then, of course, there exists some disk around, so such that if I take the disk around R, that's also going to lie inside K. Okay, so I'll just write it, rather than use a lot of notation, I will write this. Okay. In fact, Right, okay, that's fine. But remember that this was a countable, this was a dense subset, the BJs that we had chosen. We have an open ball inside. So we've thrown away all these disks, we've taken something in the complement, and we've somehow managed to find a little disk around that that's also in the complement. And because the BJs are dense, of course, there's going to be some BJ that lies inside this open set. So then there exists some, let's say, k in n, such that bk is going to lie inside the disk centered at z of radius r, which all of this is sitting inside this set over here where we've thrown away all these disks. But how had we chosen these centers? So either bk is the center of the kth disk. I mean, how are we choosing the kth center, right? So we were sort of choosing the first point in the sequence that does not lie in the previous disks. So either it's already it's already been chosen by the kth stage, and somehow if that's not happened, so we are choosing k at the kth stage. So let me write it this way. So either we have already chosen it before the kth stage, and why would this happen? So for example, maybe B2 is already in D1 and B3 is already in D1, and so we've gone all the way up to BK, so it's made it to one of these disks, or it will definitely get chosen. If not, then it will definitely get chosen at the kth stage. Okay, so this dense set, we found an element of it in this disk over here, open disk, which lies in the complement of, it lies in the interior of our set. Remember, the interior of our set is in the complement of all these disks we have removed. We have found a BK over here. Now this BK was either chosen as a center at some point of time, or it was already, if it was not chosen as a center, that is because it was already in one of these disks. So either it's the center of one of these disks or it was already in there. And if not, then at this stage, if this lies outside of all of these, then at this stage, this was chosen as the center over here. So in either case, BK is in the union of these, which is a contradiction because this BK was chosen to be in the complement of these, the union of these disks over here, okay? And so what we have shown is that whatever we have constructed, it has no interior. Okay, I can erase this. Any questions? So, well, what we want to show is whatever this weird set is, somehow there is some continuous function. So let me just write this. So since interior of K is empty, the set that we care about, the space of functions, is just CK. Okay, so what we are going to do is we are going to actually produce a specific function that's here, but it's not approximable by rational functions. So for this, what I'll do is, so first we will orient the boundaries of all these DJs counterclockwise. And of course, we will do some sort of counter integration. So given f in CK, define, let me call this function phi of f. And what I'm going to do is I'm going to integrate this on the boundary of the unit disk. And because I have oriented these counterclockwise, I sort of also integrate these on the boundary of these other disks I have over here. Okay, and what allows me to write this sum over here, remember we made a very specific choice of these rj's over here. So if we do this estimate, so I just take absolute value over here and then I sort of pull it in using triangle inequality, and then remember I will also get arc length measures over here. So what I'll get at the end of the day, I will get the sup norm over k. Remember all of these are sitting inside k, all these boundaries are sitting inside k, okay? And I have 2 pi, which is the length of this curve, plus 2 pi times summation rj over here. And all of this is finite. So this quantity is finite. Okay, so what I actually have is a continuous linear functional on this Banach space over here. But we'll come to that language in a bit. We don't immediately need that. And so how do we finish this argument over here? So suppose, so what does this mean? It means that if I have, so let me do the following. So let f be equal to the function z bar. Right, I think this should work. Okay, and this is a continuous function on k, f of z equal to z bar. And we can check, so if I compute phi of this function f over here, so I'm going to get a bunch of integrals involving z bar. This is boundary of dj. And each of these you can compute, you're going to get, so if you do this computation, you're just going to get 2 pi times the square of the radius. Okay, so this is check that when you integrate z bar on the boundary of a circle, so here you'll just get 2 pi times 1 square, but here you will get 2 pi times rj square summation j going from 1 to infinity. And because we had chosen summation rj to be less than 1, summation rj square is also strictly less than 1. So all of this is strictly greater than 0. Okay, so we're not actually interested in the precise quantity, but this is a non-zero quantity over here. On the other hand, if there exists a sequence of rational functions, let's say here, such that, and actually this is not the correct, so let me use a notation that I haven't defined because Rk for us is the closure, but let's just say these are the restrictions of rational functions such that Rn converges uniformly to f on k. So if we did have uniform convergence of Rn to f, by this estimate over here, what would have to happen? We would have to have that limit n tending to infinity, phi of Rn is equal to phi of f. Okay, we would have to have that. But if you take a rational function, remember these rational functions don't have poles on the set. So what will happen is it could happen that some of the poles are over here, but there are only finitely many poles. And you're integrating the function on the complement. So you're sort of integrating it on this. So if you look at, let's say the poles are in these circles, the integral on these circles is anyway going to be 0. So only finitely many of these terms are going to remain when you integrate a rational function. And when you do that integration, you're integrating a holomorphic function on a Jordan domain, you're only going to get zeros over there. So this is all 0, and this is not 0 over here. Okay? And so this is a contradiction over here. That completes the proof. Questions? Clarifications? Yeah, sure. So you take one rational function. Okay, so how does this go? So let me do it here. So if you look at R and Z, this is just a rational function and it does not have poles on K. Okay, so it could have poles in these disks that you have removed, but it only has finitely many poles. So its poles will land in finitely many of these disks. So on any other disk where the pole is not contained, so if I integrate R on this circle, it's just it's a holomorphic function in the interior, so there I'm just going to get a 0, right? So most of these, all but finitely many of these terms are going to drop out. The rest of them, which is this, in this picture it's these 4. So I'm integrating so what is the domain? I have this disk, I'm integrating counterclockwise on this, and then I'm integrating clockwise on this. Right? So again, I have a Cauchy's theorem which tells me that it will vanish, the integral will vanish. Does that make sense? Yeah. All right. So this, as I said, you can change the this picture a little bit. You can make sure that there is some interior, but something that I want to point out over here, maybe I'll say it over here, because yes. Right, so that's exactly the comment I was trying to make over here. So when you say measure, you mean a Lebesgue, right? So I'll use the word area, so note that the area of K is positive, right? Because I have pi minus summation of pi r square, and I've chosen r squares to be strictly less than, the summation of that to be strictly less than 1. So this is the Lebesgue area, by the way, if you're wondering what this is. And this is crucial over here, okay? So I'll sort of, that's where I want to be headed with this, but it's, if you try to do this by making the area of this set, so you can try to do this, you can try to play around with this example, you can try to tweak it. So one thing you can try to do is tweak this example so that you still have something left in the interior, and you have this lack of approximability that we established here. Another thing you can try and do is actually try to make the area of this set 0. So try to remove all of the area and then see if you can cook up something like this. Okay. So why did I make this comment over here? So I want to do a very, very special case of Mergelyan's theorem. And as I said, I sort of want to give you the basic functional analytic objects to set up this proof. So functional analytic approach. And so for this, I need some facts, which you will see in a functional analysis class, or you may have seen it in some other context. So the first one, so I sort of already used these words, right? I already said that this capital phi is a continuous linear functional on this Banach space Cx. So Cx is a Banach space. If you look at its continuous dual, what is this? This is the set of all Radon complex measures. So not x, k on k. K is compact. Okay. So we are going to use this fact by Radon. This is a locally finite regular Borel measure. So this is going to be one of the ingredients, and then what we want to show is that we have some subspace, and we want to say that the subspace is dense in this full Banach space. So how can we exploit this language over here? Okay, so given a subspace, let's say f of Ck, and a measure, So now we are identifying the dual space with the space of all Radon complex measures. So given a subspace and this measure, we say that we use the following notation. So mu annihilates F if when I do this pairing, I always get a 0. By the way, here what is the pairing? So I have a function f, I have a measure mu. I just integrate f against this measure on k. That's the pairing over here. And so if I have f d mu equal to 0 for all f over here. By the way, this is the Rees representation theorem. If you haven't seen this before but you would like to look this up, one version of this. And here, how can we exploit this? So we have this space of functionals which completely kills this subspace over here. If the closure of this was a proper subspace of Ck, okay, so what we want to say is whether the closure of this space is Ck or not. If the closure of this was a proper subspace, then the Hahn-Banach theorem would tell us that we would be able to construct a measure which kills this but does not kill the full space. Okay, so how am I going to use this fact? If, and this is the same thing as with the rational hull, these are statements which are sort of logically hard to say. How do I say this? If, okay, I'm going to say it the same way I did it over there. If whenever mu kills f, we have that mu also annihilates the full space, then in fact the closure of this space must be Ck, and this is using the Hahn-Banach theorem. What does it mean for a measure to annihilate the full space? We have a Radon complex measure supported over on K, so this is just the same thing as saying that this is just the 0 measure. Okay. So what is the idea over here? What is the technique? I have some subspace, restrictions of polynomials or restrictions of rational functions. I want to say that the closure of that space is all of Ck. I take all those Radon measures which kill this subspace, and then I show that that measure must be 0. Okay, so if I can do that, if I can start with any such measure and then show that I have no option but that measure is 0, then that tells me that in fact f is dense in Ck. That's the strategy over here. Okay, so that somehow a lot of the one variable approximation results, they sort of all fit this regime over here if you try to do something like this. Questions? All right, so we'll demonstrate this and we'll sort of introduce a gadget that helps us do something like this. And this gadget is very, very useful in one variable complex analysis. It has a lot of, it's very powerful, and there's like an entire section of several complex variables where there was an attempt to try and find some object like that in higher dimensions. So what is the result that, what is this special case of Mergelyan that we are going to prove? So let's call it theorem, and it's a special case. Let K be compact such that C minus K is connected and K has 0 area, so it has Lebesgue measure 0. Then we are going to show that AK is equal to PK. In fact, there's no interior, right? If the area is 0, how can it have interior? So CK is equal to PK is what we are going to show. This is how this entire functional analytic discussion is going to be useful. So I have assumed that the complement is connected. Without this condition, and with an A over here, this would be the full Mergelyan theorem. But here we are doing a very, very special case because we are sort of able to do this fairly easily. So I'll sort of demonstrate this case. And by the way, if I do not put this condition, if I don't ask that the complement is connected, you can actually also get rational approximation over here. So you're never going to be able to construct, if you assume that the area of the set is 0, you're never going to be able to construct a Swiss cheese kind of a counterexample. So as an exercise, take the proof that we are going to do, remove this condition from that, and just try to show that you can actually get rational approximation over here. Okay? It's sort of an extension of the same idea. All right, so proof. How much time do I have? Okay, great. So let alpha mu be a Radon measure such that alpha kills all polynomials. So I can even do this. We will show that alpha has to kill all continuous functions. Sorry, I'm bad with this. Okay, we'll show that mu has to be 0. That means it kills, and that sort of tells us that pk has to be ck. And the object, the gadget that we are going to use is known as the Cauchy transform. So let C, I'll use this script C of mu, and I'm going to evaluate, so I'm going to construct a function, and here Z is going to come from the complement of K. Okay, so it's going to come from the complement of K, which remember is a single connected component. We only have one connected component. And what is this object? I'm going to look at d mu w divided by w minus c, and then you do this integration on c. But remember that the support of mu, it's a Radon measure on K, the support of mu is actually on K. So a priori you might think that this is a problem, we have this singularity. Well, is it really, I mean, sorry? So, I mean, it's not really a problem anyway, but here our z, our w is coming from K and our z is coming from the complement of K. Okay, so from what I just said, check that C mu is well defined as a function and is holomorphic on C minus K. So remember that this is the variable z over here. You want to show holomorphicity of this, so you need to make sure that you can differentiate under the integral sign or whatever technique you want. Yes. Well, okay, I can integrate over C, but the support of this measure is K. So this integral is actually taking place on K. Because just, I mean, it doesn't matter. I can write the same thing. So maybe in green, I'll write K over here in bracket, so that you know that this integral is actually taking place over K.
Even if it is, you can define inside K also.
Why is that?
Because this is R2, so it is removable.
Good. So this singularity is actually not a problem over here. So you can check that. We don't need that, thankfully, in this proof. But if you want to do sort of the more general case over here, and in general, when people study the Cauchy transform, it does really matter what's happening on K as well. But we'll sort of not worry about that. For our purpose, this is good enough. Okay? Of course, the holomorphicity becomes a problem when you do that, when you try to extend it past K. Okay. So what do we now have? Our ultimate goal is to show that mu vanishes. So how can we exploit this object that we have constructed? So let me write its name because it's a really important, so Cauchy transform of mu. Okay, that's this object that we have over here. And yes, so how can we use this? So we are yet to use the fact that mu actually kills all polynomials. So we have this compact set K. We have assumed its complement is connected. All your W's are coming from here, and then my Z is coming from outside. Now, if absolute Z is greater than absolute W for all W in K, So maybe this is the origin, and maybe I sort of take z that is coming outside of this ball, then I have an expansion, right? I have 1 over w minus z, and I want w over z to be less than 1. So I pull out minus 1 over z, and I get, so I'm going to do this slowly because I'm always, so I have an expansion. Okay, so I have minus 1 over z, and then I have summation w over z to the j going from 0 to infinity. So for a fixed z such that star holds, this expansion or this series converges uniformly. Now let's be careful. So z is fixed, and we are taking this series in w. We're talking about the convergence of this series in w. So converges uniformly in w on all of k. Z is fixed like this over here. So then what do we have? Remember that this is taking place on this is really taking place on k, this integral. So thus, if I look at c mu of this z, what I'm doing is on k, remember this integration is happening on k, I'm really integrating d mu of w against this over here. So I pull out the minus 1 over z, and then I have summation w over z to the j. I mean, this is absolute and uniform. I can sort of pull everything out. So let me write this a little bit better. I have minus 1 over z, summation j going from 0 to infinity, integral d mu w against w to the j divided by z to the j, and this is all happening on k. But as I had done previously, I can write this, I mean, I can also write this as c, because the support of mu is on k. But, okay, what do we use over here? So what was the property of mu? What had we started with? We had started with something that kills polynomials. So what am I going to get over here? These are all just polynomials in w, right? And mu kills all of these. So this is all just 0. So I have this holomorphic function, c mu, and outside this ball, it's all 0. Okay? And remember the complement, the complement of this ball is sitting inside the complement of k. I have a holomorphic function in the complement of k. It is 0 on an open set over there. So by the identity principle, it has to be 0 everywhere. So what we have, but we are not quite done. All we have shown, I mean, what I was interested in showing is that the measure is 0. I've cooked up something related to this measure. I mean, who knows what the Cauchy transform does. So since c mu is holomorphic on c minus k and vanishes on some open set in c minus k, in fact, c alpha c mu is 0 on c minus k. Okay? So we have this function. We don't know anything about this function on k. Even if we can define it on k, we don't know if it's going to be holomorphic there or not. But outside of k, it is holomorphic. In fact, it's identically equal to 0. And what we do know is that the Lebesgue measure of k is 0. That was our assumption. So how are we going to use these two facts to show that mu is equal to 0? Okay, that's our ultimate goal. And so for this, so this is the final trick, which is also very useful every time you're working with the Cauchy transform. This is how you sort of exploit the Cauchy transform. So to show that mu is 0, we will show that, so how can I show that a measure is 0? I'm going to integrate it against all sorts of test functions. So my test functions are compactly supported smooth functions on C. Okay? This is how you show that a measure, a Borel measure like this is a zero measure. You sort of hit it against all test functions, and if you can show that you always get a zero, how much time do I have?
Still 10 minutes.
Sorry?
Still 10 minutes.
Oh, still 10 minutes. Okay, great. Right. So if I can show that I always get a zero like this, then I have shown that the measure is zero. Okay. So how do we relate this to the Cauchy transform? So this is sort of the final trick. And for this, we sort of use a better version. So I'm hoping that many of you have seen this. If you have not, this is really sort of the correct way to think about, I don't know, correct, but it's sort of helpful to think about it this way, which is the generalized Cauchy integral formula. So we are really just using one variable tools, but we have to use the correct object. So I mean, this is also known as the Cauchy-Pompeo formula. And maybe some of you have been introduced to the Cauchy integral via this. And how does this go? So this is how it goes, since I have time. Let's say that I have, how do I want to do this? So let me just state it for, so let omega be a smooth bounded domain in C, and let G be a smooth function defined on a neighborhood of omega closure. Okay? So I'm just, I mean, this is probably not the most sophisticated version of this, but I'm just writing enough so that we can apply this. Then, so I have some bounded smooth domain. I'm going to orient the boundary sort of in the standard way. And then I have a function which is sort of smooth beyond the boundary of this domain. Then, so we start with the part which looks like the Cauchy integral formula. But I'm not assuming anything about the holomorphicity of this function. Okay, so this should already make you suspicious. And let me make sure I use the correct variables, because I do tend to mess this up. So I have z minus w. And then to sort of compensate for the fact that this is not a holomorphic function, what you have is you have this integral which is a solid, this is a boundary integral, but this is sort of a solid Cauchy integral. And here you take the z bar derivative and you integrate that against the Lebesgue measure, but you use the same kernel. You use the Cauchy kernel, 1 over w minus c. So this kernel is very interesting because it can appear in these sort of curve integrals, but it can also appear in these solid integrals. And it does different things in different settings. And this should sort of indicate to you that we are heading towards the Cauchy transform. Okay, this should remind you of the Cauchy transform. So we have this formula. Of course, if G is holomorphic in the interior, this drops out. You get your Cauchy integral formula over here. Okay, that's why we are calling this the generalized Cauchy formula. And you can, this is some sort of a green, like one of these various green identities you can use to prove this. If you want that as an exercise, you can prove it if you know enough multivariable calculus. I mean, it's just another form of Stokes's theorem at the end of the day. Okay, so I know that's a lot of stuff, but we will now finish the proof using this machinery over here. What do we want? We want to start with a compactly supported smooth function. We want to show that its integral against mu is 0. So let G be a compactly supported function and B be a large ball containing the support of G. Then G of Z, here by the way Z is coming from the domain, of course. So G of Z in the interior, so right, containing support of G and K. So this ball also contains K. So it contains a K and it contains your support of G. So what we get over here is we get the integral, and we are going to apply the Cauchy-Pompeo formula to some large ball containing both these sets. I get 1 over 2 pi I over this ball, Z minus W. Remember that the support is contained inside the ball, so this term is not really, the function is really 0 over here, but I have this other term which is important. I have some derivative over here, W minus Z, Lebesgue measure W. And this is happening over this ball B, which contains both the support and K. And now what I do is sort of a swap of integral. So now I integrate against d mu, because that's what I wanted to check. This is not there. I have d mu Z. And now you need to go back and think why this is justified, but I can sort of swap. So I'm going to pair this kernel, I'm going to pair this kernel with this measure. And so what I'm going to get is I'm going to get the integral of something, which is a nice object, times the Cauchy kernel of mu against, sorry, so this, yeah, so I get in W against the Lebesgue measure in W. Okay? And this is all happening on C, but this is 0 almost everywhere. This is a 0 Lebesgue almost everywhere. So all of this is just going to be 0. And that, I mean, since we started with an arbitrary test function, and so we have finally got that mu is the 0 measure. Okay? So sorry, I went over time, but I'll stop here. Yeah, I'll stop over here. You can check the notes if you want a little bit more detail. Thank you.